alkyl halides undergo the nucleophilic substitution reactions. We know in the alkyl halides you can remove a halogen atom by a nucleophile. So on this particular topic, let's practice certain questions. Here we got a first question. Alkyl halides, they can undergo the nucleophilic substitution either by the SN1 mechanism or the SN2 mechanism. In the SN1 step, what happens first? It is the loss of halogen. We know that, in a SN1 mechanism, that a halogen atom which is there is being replaced from the carbon, and what you get a carbocation there. So this is the step number one, and in the second step, it is the nucleophile that actually attacks on it and forming the product. So that means in the first step of the SN1 mechanism, it is the formation of a carbocation that takes place, and this step is actually the slow in the mechanism. The second step is the fastest step. So that's why the rate determining step in this case is the first step. So that means in this question, option C is the correct answer. Now we have different types of alkyl halides. If you look at here, this is a 1 degree alkyl halide. This again a primary one. This one is a secondary alkyl halide, and this one is tertiary alkyl halide. And the question is, which of one of the following compounds most readily undergo the substitution by the SN2 mechanism? What actually happens in the SN2 mechanism? In the SN2 mechanism, we know that in this case, if you have a halogen, a nucleophile approaches from the back end of this halogen, the leaving group, which is actually here a halogen, and it forms a transition state. But for a nucleophile to approach to this particular carbon here very close, we need the groups around this carbon smaller in the size. And generally the primary alkyl halides, if you have suppose one alkyl group and two hydrogens, or if you have three hydrogens only, so that means only 1 degree alkyl halides, they actually prefer the SN2 mechanism, because the crowding is not too much. If you have a bulky size over here around this particular carbon, then nucleophile will find it very difficult to approach to the carbon and replace the halogen. So that means SN1 mechanism and SN2 mechanism, it depends on what type of a substitution is around the carbon, correct? And for the SN2 mechanism, what we need less crowding around the carbon here, right, attached to the halogen. So that means the order of the reactivity of the alkyl halides is basically 1 degree alkyl halide. Okay, 1 degree alkyl halide prefers this SN2 mechanism, and then secondary will be less and the tertiary will be the least one. So I can see the order of reactivity will be primary, secondary alkyl halide, and then the tertiary alkyl halide. And for the SN1 mechanism, what actually happens in the SN1 mechanism? We learned that it is the formation of a carbocation, and we know that tertiary carbocation is more stable, right? In our last question over here, what we learned that it's the carbocation which is formed as an intermediate in the SN1 mechanism, correct? In the SN1 mechanism, carbocation is formed, and this will be preferred if you have three alkyl groups over here, because the tertiary alkyl halide will produce a tertiary carbocation which is more stable, right? So that means for the SN1 mechanism, you should have three alkyl groups. So that means tertiary alkyl halides, 3 degree alkyl halide prefers the SN1 mechanism, and then the secondary will be the less, right? And then the least will be the 1 degree alkyl halide. This will be the order of the reactivity of the alkyl halides towards the SN1 mechanism, and for the SN2 was that 1 degree more than secondary, then the tertiary. So that means the order is reversed. For the SN1, it is a tertiary that actually prefers it, okay, and then a secondary alkyl halide, and then the 1 degree alkyl halides over here. So in this case, if you look at here, the alkyl the alkyl halide that prefers actually the SN2. In this case, we got two alkyl halides, but again, you see this is the 1 degree alkyl halide. This one is also 1 degree alkyl halide. But look at here again. If you look at this particular carbon, which is attached to the isopropyl group over here, so that substitution, is little more. Size is, bigger over here. And if you look at here, we have a carbon that's attached with only the methyl group. So that means that, the repulsion will be least in this case, okay? The least, repulsion between the nucleophile and the alkyl group is minimum over here, okay? So that means it will be the preferred, alkyl halide that follows the SN2 among the 4 options are available here, correct? So the B option here. Let's take another question. The reaction of the methyl bromide with the hydroxide replacing the bromine with the OH. So we know that this is the SN reaction because you are replacing the bromine by the OH, correct? Okay, one nucleophile replacing another nucleophile. But what will be the mechanism? Is it SN1 or SN2? We just learned that if you have a very less crowding around the carbon, right? Okay, less crowding around the carbon. Suppose this is our halogen bromine, and the nucleophile over here, in this case, when you have 3 hydrogen atoms, the repulsion between these alkyl, these hydrogen atoms and the nucleophile will be the minimum, will be the least here in this case, correct? Okay, so that means this nucleophile can easily approach this carbon and knock out the bromine over here. So that means the mechanism will be what? It will be the SN2. SN2 will be preferred because you don't have too much of substitution around the carbon. You don't have bulky groups around this particular carbon. If you got suppose 3 alkyl groups over here, right? So then this thing will be impossible, right? Okay, the nucleophile will find it very difficult to approach to the carbon, so SN2 is not preferred. For that case, SN1 will be the the mechanism. But since we have here only 3 hydrogen atoms over here, so the best mechanism, the lowest energy mechanism for this alkyl halide will be the SN2, correct? So the option B here, SN2 mechanism. Now let's take another question over here. We got a secondary butyl chloride, okay? Secondary butyl chloride, this is our butane, and if you put over here a chlorine atom over here, so this is a secondary butyl chloride. And look at this alkyl halide now. It's again a secondary alkyl halide. It's a 2 degree alkyl halide, correct? Because you see there are 2 groups. One is this one and one is this one, right? Methyl and ethyl around the this carbon here. Now again, what we learned that for the SN1 mechanism, the order is tertiary, secondary, and then primary. For SN2 mechanism, we learned 1 degree prefers, 1 degree alkyl halide prefers more than the secondary and then the tertiary, okay? And then the tertiary over here. Let me rub it first. It is tertiary over here, 3 degree. So over here, in this case, what we have a secondary alkyl halide. So basically, the secondary alkyl halide, it can undergo the substitution by SN1 and also the SN2 here, right? So both options are possible for this alkyl halide. So that means we can say in this case, for this particular question, it says that the secondary butyl chloride undergoes alkaline hydrolysis in the polar solvents by which mechanism? Is it only SN1 or only SN2? No, it's both SN1 and SN2. But remember one more point here, very important point. When you carry out a secondary alkyl halide in the polar solvent, right? Polar protic solvent. It's very important here. Polar protic, and you have a polar aprotic solvent, correct? That is another important factor. In this case, it only asks us what will be the mechanism. We can say it's both. But if you have a question, which one will be the major product? Will it be the SN1 dominant or the SN2? Actually, you don't have a 50-50%, not like that, correct? It depends on the solvent, what type of solvent we have here. Simply it says the polar solvent, so we can say it will be for the both. But if it elaborates here in a polar protic solvent, then what will be the dominant one? In a polar protic solvent, it is the SN1 which is the dominant product. And in a polar aprotic solvents, if it asks us here polar aprotic, then it will be the SN2. So you have to be a little careful here, right? So here in this case, it simply says the polar solvent, that means it will be the substitution SN1 and SN2 both, correct? But if you have to be a little precise, polar protic or polar aprotic. So polar protic means, when you have a solvent like water, a solvent that contains the hydrogen, okay, so that can be replaceable, okay, H positive ion, and solvent that can produce H positive ion, that's called a polar protic solvent, right? So in that case, it will be the SN1, and polar aprotic, it will be the SN2 mechanism, right? So now another question over here, we have alkyl halide and you react with the aqueous, not the aqueous, sorry, it is alcoholic, very important, potassium hydroxide. So what you will get? So again, you have to be a little more careful. If you react with the potassium hydroxide in aqueous medium, okay, aqueous medium over here, then what you get? You will get a dominant product will be here, a substitution, nucleophilic substitution product will be here. That means you will get alcohol. Hydroxide, chlorine, or whatever is the halogen over here, that will be replaced by the hydroxide and you will get alcohol. So you will get, that means the product will be the alcohol. But if you take it, if you take this alkyl halide and react with the KOH in what? In an alcoholic medium. Okay, this is little less, polar solvent, okay, than the water. In the aqueous is very much polar. But if you carry out the reaction in the alcoholic medium, and there what happens? It is the dehydrohalogenation. Elimination reaction is the dominant one, right? So hydrogen will be replaced from the beta carbon, and halogen will be replaced from this one. So then you will get actually an alkene, correct? And we have learned that if you have two types of products possible, and what will be the alkene? Which alkene is dominant one? We've always follow the Sartzef rule, isn't it? And the Sartzef rule says that an alkene will be dominant which has more substitution, correct? An alkene that has more substitution around the double bond, carbon-carbon double bond, that will be the dominant one, okay? So look at here, what are the options available as? It says this is dominant, okay? This double bond over here, and you have two methyl groups. In this case, you have double bond and you only have a one alkyl group. So if it is a halogen like chlorine or the bromine, right, or the iodine, then you can easily say that this one will be the product, because that is as per the Sartzef rule, right? As per the Sartzef rule, this should be the the dominant one when we have a chlorine, chlorine, bromine, or iodine. But if you have a halogen over here, if the halogen here X, it is fluorine, right? In that case, it's not the the Sartzef rule. It's not the Sartzef product which is dominant. Okay, I'll repeat it. With the fluorine attached to the carbon, it's not the Sartzef rule that will give you the dominant product. Rather, it is the Hofmann, okay, Hofmann rule, that will follow. And we know what happens in the Hofmann. Hofmann elimination is, that says that, in the Hofmann elimination, an alkene with less substitution is a dominant product. Correct? So we have actually two principles here. One is a Sartzef rule. One is Sartzef rule, the other one is Hofmann, okay? Hofmann, product. Sartzef rule says, alkene with more substitution will be the major product, but that's only when you have, the halogen like chlorine, chlorine, bromine, or the iodine, right? But if it is very strongly electron withdrawing, group attached to the carbon, just like we have fluorine, okay? Like the fluorine. And among the halogens, this is the only exception. Remember, only the exception is fluorine. There are some other groups, but among the halogens, this is the only exception. When halogen is attached there, the Hofmann product is a dominant product there. Correct. When it is chlorine, fluorine, or the bromine, it is a Sartzef product. And what we know from the Sartzef product, alkene with more substitution is dominant. Right? That is the major product. And Hofmann, it says that alkene with less substitution is dominant. So which option over here is correct? So you can, it looks like this is also dominant, this is also correct. Both are formed in equal amounts. No, that's not, that's never possible. The product ratio depends on the halogen, Okay, it depends on the halogen over here, right? So that means, what will be the major product actually? We have to see what type of halogen is there. Is it a fluorine? If it is fluorine, then this will be the major product, correct? And if it is chlorine, bromine, iodine, then this will be the major product over here. Hope you got it. Thanks for watching the video. Bye for now.